Welcome to the next lecture in the series of the course Quantitative Methods in Chemistry. So let's quickly recap what we saw in the previous class. We defined a few terms. So we wanted to seek the truth in way of experiments, and experiments fetches data, and we are trying to understand how data can be analyzed to, of course, go back to understand the truth. In this aspect, we defined a few terms. We tried to understand what was the Galton's experiment. We understood the fact that random errors have or display a normal or a Gaussian distribution. The Gaussian distribution, let us say a function f of x, is defined as 1 over sigma times square root of 2 pi e power minus x minus mu the whole square divided by 2 sigma square, where sigma is the population standard deviation, mu is the population mean, and basically this is a normalization that constant that goes, and this is the basic distribution. So what this means is that when you are making a measurement, you have a probability of getting your data point within this distribution, and that is determined, or that is kind of indicated by the standard deviation that comes in. And we learnt that measurements within one standard deviation correspond to about 68% of data, within 2 standard deviations correspond to 95% of data, and within 3 standard deviations correspond to 99.7% of data. So this gives you an understanding that if you do get numbers, where can it fall and what does it mean? Okay, so we were talking about population versus a sample. Population represents a large set, but not always we have the luxury of getting the data of the entire population. So what we end up doing is to sample a subset of this population. So therefore we assume that the sample does represent what the average population is also representing. Of course this is an assumption, but not always we have the luxury to perform infinite experiments. So therefore the sample is what we have to use in most of our, or employ in most of our experiments. So now that we have understood it, so basically let us say you are acquiring data in terms of the fact that when you set up an experiment, you have a stimuli, meaning that you perturb the system and then you get a response, and the response is what is measured in terms of data. It could be a spectroscopic technique, it could be a concentration measurement, it could be anything of that sort. Okay. So now when we have this data, we defined a few terms here. We defined what is the sample mean. The sample mean was defined as x bar is equal to summation over xi divided by n, with I from 1 to n, where xi is the data and n is the total number of measurements. Okay. And the only difference between sample mean and population mean is in the fact that n is large for population mean while n is small for the sample mean. Of course, population mean goes with the formula mu, which we just saw a moment earlier in the Gaussian distribution. And the other definition that we laid forth was the standard deviation. The standard deviation is nothing but the square root of variance. Variance is sigma square root of variance, and this is defined as the square root of deviations of each data point from the population mean to that of the number of measurements. Of course, when it becomes a small data set, it becomes population standard deviation. So, that will be given as square root of sum of xi minus x bar the whole square divided by n minus 1. Okay, so these were the definitions that we saw in the previous class. Let us ask a simple question to start with. When you are talking about data and when you are talking about percentages, if we make a single measurement, what does that mean? A single measurement just means that your data could fall within any part of this distribution, and basically the standard deviation gives you how probable will it fall as close as to the mean for that given measurement. And remember, the mean, the population mean is what helps us seek the truth. Let us say if the concentration of a given chemical, the mean of multiple measurements should be very close, or actually is the concentration of the chemical that you are seeking. So, now if you are able to do good number of measurements, if you are able to do, let us say 1000 measurements, it becomes a population a standard deviation, while if you are able to make only 10 such measurements, it becomes sample standard deviation. So, this was the example that we saw in the previous class. I will already start showing you glimpses of how to use Excel in order to make your analysis easier. Here what we see is that we can calculate average and standard deviation, and these are the data points that you have as the that you ended up measuring. So, the example that we took is aliquoting 2 ml of water from burette in order to calibrate the burette, and what you are able to see is small changes that come up. Instead of taking the burette, we can take an example of a micropipette which can aliquot 2 ml out. So, the average basically is nothing but the sum of each one of this. It can be done by the sum as in this fashion. Divided by the total number of measurements, in this case 10. So, that will be the average, and you get a number like 1.9962, and the standard deviation of course will be nothing but square root of difference between a given number minus that of the average that you have determined. This is the sample mean that you are having. So, that's a number that's not going to change. So, that's going to be $L, $2, indicating that keep that value constant, the whole square, plus of course you are going to do C2 minus the whole square, and so on and so forth, going until K2 minus $L, $2 the whole square, divided by n minus 1, which will be 9. So, the sample mean is given by the sum of all the cells that contain the data that has been recorded divided by the total number of measurements, which is 10 in this case, while the sample standard deviation is nothing but square root, the function that is given in Excel as sqrt, within B2 minus L2, where L2 is the sample mean, while B2 is that given measurement. So, this is nothing but xi minus x bar the whole square given as the exponent 2, similarly going until K2 divided by 9. So, now that we have determined this for the first cell, doing this with a computer for all the other students or the other data sets is straightforward. You just copy paste the formula, you are able to get the average and standard deviation for each of the student independently. And what you are able to realize is that within the single standard deviation, almost all the averages work out with each other. However, there are variations that come in the sample standard deviation. Just before going ahead and understanding and analyzing this data, there are also easier ways of doing this with a software like spreadsheet. So, here instead of typing each cell and getting sum as that way, you can do a sum and select all of these cells in one shot divided by 10. That is also going to give you the average. On the other hand, there are functions that have been written in Excel spreadsheets which will help you determine this more easily. For instance, the average of these numbers, which once again is given by average times this, will also give something similar. So, instead of typing the formula of mean every time, you can use the functions that already exist in Excel. Similarly would be the formula for standard deviation that goes as STDEV, and then select the number of cells, and you get the same number as we have used the formula. So basically we have introduced the formula stepwise to you, but at the same time how to use spreadsheets to get the answer relatively quickly as well. So now that we have gotten this, let's try to understand, instead of using 10 data points in each one of this, what happens if you use 20 data points at a given time. So here let's take a look at the average and standard deviation for 20 data sets at a time. So let me merge the cells to say 20 sets at a time. So here I am going to say average and then select these 20 cells, and then similarly standard deviation and these 20 cells. So what you are able to realize is that the standard deviation starts to represent more data sets, and the average still hasn't changed much. So let's now copy paste this once again, where it uses 20 data sets at a given time to see how this varies. One is able to once again appreciate the fact, okay, the standard deviations once again are very similar, right? So if you keep on changing the 30 data sets, 40 data sets, what happens is the question. So one has to remember that this is called the standard error of the mean. Meaning, if you have S as the standard deviation and the standard error of the mean is given as SM, the standard error in this case will go as S divided by square root of n, where n is the total number of measurements. So this indicates the fact that as you keep increasing the sample size n, your standard error of the mean keeps reducing. However, it doesn't reduce too fast, meaning that if you want to half your error, you need to increase the number of data sets by 4, and if you want to reduce your standard deviation even more significantly, you have to go with the square of the precision that you would like to get. Okay, so now rather than doing this, as you are able to see, to reduce this is more difficult. So people tend to set up experiments such that the standard deviation that comes up is already low. We will be seeing in the next week how this can be done. So basically this helps you understand how experiments are set, and one can also understand that the more number of repeats help you get a better estimate or the reality that is closer to the truth. So instead of taking the 10 data sets at a time, we have 50 students in this example, and each student has 10 measurements. So why don't we take all the 500 data points at the same time? So I am going to say average of all these cells and standard deviation of all these cells. And what you are able to realize, this comes up to be 0.1. Okay, so you have subtle variations that come when you have less number of data sets, but as you start using more and more number of data sets, you tend to get a proper representative of the population from the sample itself. Okay, now that we have understood this, let's try to define a few more terms. The next term that we'll be introducing to define your data is called the median. Median is defined by the fact that, let's say you have a set of numbers xi, if you arrange them in the ascending order, meaning that from low to high, what is the value of the number that comes up in the middle? For instance, let's say you have numbers x1, x2, x3, x4 and x5, and these are your 5 data sets. So here capital N is set to 5, and you have been able to make 5 such measurements. Here the median will be the number that comes in the middle. So now let's say we have another data set that goes as x6, x7, x8, x9 and x10. So in this case we saw an odd number of measurements. Let's say you have an even number of measurements. In this case what ends up happening is that you calculate the median by taking the middle two numbers and averaging them. So basically median in the odd case scenario is that, let's say you have n measurements that are odd, you tend to go n plus 1 by 2 to determine the median. So, in this case you had 5 measurements, so 5 plus 1 by 2 is 3. So, therefore, you took x3 to assess what is the median. If you have even number of measurements, then you take the average of the data sets that you got for n by 2 and n by 2 plus 1. So, in this case you are going to have, what is n by 2? You have 10, 10 by 2 is 5. So, you take 5 and 5 plus 1. So, you take the 5th and the 6th point to get what is your median. Why is this important? Not always you are going to have a case where all numbers are equally represented. Let us take some examples where you tend to have a few measurements done in this way: 5, 6, 7, 11, 12, 13 and 15. So, when you have made these measurements and these are already ordered in an ascending order, let us quickly determine what is its average. The average for this case is going to be given by close to 9.9, while the median that we will end up measuring. So, you have 1, 2, 3, 4, 5, 6, 7 measurements. So, basically it is an odd number. So, you go 7 plus 1 by 2, which is the 4th element. So, 1, 2, 3 and 4. So, you are getting a median as 11. This matters a lot, largely because maybe you are looking at the age of students within a given room or in a creche facility in months. So, what is going to end up happening is that you have numbers that go as integer steps, but you get an average that is about 10, but you are able to see the median that is falling away from the mean. That indicates the fact that the middle of the distribution actually does not fall in the mean, and there is quite a amount of variability that comes. Of course, we have already defined that as the standard deviation that goes. So, I leave it as an exercise for you to find the standard deviation, but my guess would say the standard deviation would fall somewhere at 2. Okay, so now that we have seen what is the definition of the median, let us take a look at the next definition. So, in this case we will be defining what is mode. Mode is nothing but an element that is repeated most often in the sequence of data that you have measured. So, as in the previous example, if we take a close look, you realize that none of the measurements have been repeated in 5, 6, 7, 11, 12, 13 and 15. No measurements are repeated. So, in this case mode does not exist, it is not applicable. Mode does not exist. Okay. But on the other hand, what this helps you understand is like the frequency plots that we were seeing yesterday. If you are able to find where is the mode and the mode falls very close to the average, that indicates which population is skewing the average or which set of sample is skewing the average. So, generally when you are collecting data, people tend to report mean, median and mode. If all the three agree with each other, meaning that the mean, mode and median are all close to each other, this indicates more or less a proper uniform Gaussian distribution that comes up. Okay, now that we have seen that, why don't we apply this to the example that we are seeing from yesterday's class. So, now that we have seen what is the average and standard deviation, I am going to be removing the unnecessary elements in this. So, now let us ask what is the median for this data set. So, for instance, let us take one at a time. So, let us take this data set. Similar to the functions that I introduced in terms of average and standard deviation, there is also a function written in spreadsheet generally called median, which will help you find the median of this data set. What you are able to realize is the median and the mean are very close in this example. So, let us calculate it for all the 50 students. And what you end up seeing, okay, you do see some variability, but that once again falls within the standard deviation, which kind of indicates the fact that it is quite normal distribution that you end up getting for the data set that you have seen here. This is slightly far away, but what you are able to realize within 1.9 to 2.1, all the cases fall in terms of the median analysis. So, now let us ask what is the mode. Mode once again is which number gets repeated the most within that given distribution. We are once again using the function that exists in the spreadsheet. NA stands for not applicable. But for some data sets you do end up seeing that you do have a mode defined. In this case, the mode is defined as 2.0659. Let us see whether it is indeed correct. If you pay close attention, you see two cells here that have 2.0659. That's just a mere coincidence, because when measurements are being made, you don't have to get the exact same measurement multiple times. On the other hand, do we have other examples? Yes, we do. In this case, what you are able to see, it happens in such a way that these two numbers have gotten repeated. And you realize for most of the examples, you do not have a mode that is properly determined. So now, similar to what we did for the 500 data sets, let's determine what is the median for all this data set. Of course, what you end up doing is to use all of this in one shot. Please pay attention when you are making such measurements not to choose the wrong columns that end up coming. That will come with practice. And what you are able to see in this case, the median nicely matches with the mean. Once again, this indicates that you have a good normal distribution about the mean that you have been able to get. And then let's determine what is the mode. So that's going to be equal to, this is going to be a very interesting analysis. The mode comes as 1.9402. So let's see how many times are we able to spot at least a few cases of such occurrences of 1. So you can search. So select all, then you should be able to search the data. So let's say find what? 1.9402. There you go, that is the first occurrence. Where is the next occurrence? There is the next occurrence. So basically this appears twice, and that happens to be interesting. So there are also other times that you get two sets of numbers that come in, and it tends to pick the lower number, indicating that mode in this case doesn't properly represent the mode that we are trying to look at, because there are multiple numbers. For instance, we just saw cases where these two numbers are also represented 2 times each. So one thing that you are able to understand is that when you get a data set, giving the mean, standard deviation, median would help you assess what kind of data that you obtained. Now that we have seen how a data is represented properly with mean, mode and median, and of course standard deviation, let's try to ask why are we worrying this much about it. So all these parameters are defined because when you are taking 1 mole of a substance, you are talking about 6.022 into 10 to the power of 23 particles. And this means that when you are making a measurement, the measurement is never on a single molecule, except for a few exquisite experiments which can probe single molecules. Most often you are going to be looking at an ensemble or a group of molecules, and you are interrogating all of them together at the same time. And of course, they themselves have a distribution within them. This is not new for chemists who have learnt the kinetic theory of gases, where when you plot the number of molecules that possess a velocity v, it goes as the Maxwell's-Boltzmann distribution, which is slightly different from the normal distribution, because as it goes from proportional to v square exp minus alpha v square. Here this is the Gaussian part, but you also have a polynomial part, so that makes this function an asymmetric function. But on the other hand, many other parameters that you end up measuring for an ensemble of molecules would probably end up having a normal distribution. So basically, distributions are what happening is that when you make a certain measurement, you are not able to interrogate one molecule at a time, but you interrogate the entire population at the given time, and the variable that you are trying to measure, let's say, is x. You are going to have the population of x that decides where the average falls, most often than not. So therefore, what ends up happening is that these kind of distributions help you assess how far are you from the truth. So now we have realized, if you have a data set, you would have to provide the mean, either the sample mean or the population mean, depending upon the number of points that you are able to measure. And of course, the number of points measured, n, should also be defined. Then you define the standard deviation, once again the sample standard deviation or the population standard deviation, and the other parameters such as median, mode. One parameter that also matters here is the variance, which goes as S square. For a population measurement, then it goes as sigma square. The important point that comes up right now is that most often in science we see parameters that are not a direct dependence. You are seldom going to have f of x equal to x. You end up having something like f of x is equal, a given parameter is dependent on multiple variables such as f of x comma y comma z. So, when this happens, you have a variation that comes in the measurement that you are trying to do, and that depends on the variation that comes from each of these independent parameters x, y and z. So, basically what ends up happening, if you are able to, let us say this could be temperature, this could be pH, and this could be, let us say, ionic strength. So, what ends up happening if you are trying to measure conductance, all these variables would end up affecting the final measurement. So, these are all independent variables, while conductance is a dependent variable on these independent parameters. So, what ends up happening, we are able to immediately understand that the uncertainty that will be associated with each of the parameters is going to overall determine the uncertainty of the parameter that you determine. Let us say A is equal to f of x comma y comma z, then the uncertainty with the measurement of A is going to go as a function of all of this. So, this goes back to the equation called the exact equation of error or uncertainty propagation. So, this goes as, let us say you have once again A is equal to f of x comma y comma z, then sigma A square is going to be given by dou A by dou x the whole square sigma x square plus dou A by dou y the whole square sigma y square plus dou A by dou z the whole square sigma z square. So, what you are able to realize is for each of the independent variable that is associated with a certain variance, the variance of the final measured A will be determined. Let us take a few examples and take a look at it. So, let us say A is given as x plus y minus z. So, in this case, why don't we determine what is the standard deviation that is going to, what is sigma A going to be. So, sigma A square is going to be dou A by dou x. So, dou A by dou x, remember in this case y and z are kept constant, here x and z are kept constant, here x and y are kept constant. So, what will end up happening here is that dou A by dou x is 1. So, you are going to have 1 square times sigma x square. Similarly, will be the case for this sigma y square plus. So, therefore, what ends up happening, sigma A is going to be given by square root of sigma x square, sigma y square plus sigma z square. So, what you are able to realize is, let us say that we are taking only two measurements and both sigma x and sigma y are 1 unit. Sigma A is going to be given by square root of 2. So, therefore, what it means is that although you are adding these two, the errors do not add up linearly. This is a very important point for one to understand. And at the same time, the other take home message from this example is that irrespective of whether you add or you subtract, the standard deviation or the variance that comes up ends up being sum of these. So, let us take another example. In this example, let us say A equal to x divided by y times z. So, once again let us write the formula, the exact formula of error propagation. Sigma A square is going to be given by dou A by dou x the whole square, sigma x square plus dou A by dou y the whole square sigma y square plus dou A by dou z the whole square sigma z square. So, now dou A by dou x is going to be given by z over, of course, here y and z are constant, x and z are constant, x and y are constant. So, therefore, this is going to be equal to z by y. Dou A by dou y is going to be equal to minus x z by y square, and dou A by dou z is going to be equal to x by y. Therefore, sigma A square is going to be equal to z square by y square times sigma x square plus, because the square of minus x z by y square will be plus x square z square by y square, sigma y square plus x square by y square sigma z square. So, let us divide the entire term by A or even A square. So, what will end up happening is divided by x square z square by y square. So, immediately one is able to realize when we minimize this, it is going to be sigma x square by x square plus sigma y square by y square plus sigma z square by z square. So, therefore, this reduces to sigma A by A is equal to square root of sigma x by x the whole square plus sigma y by y the whole square plus sigma z by z the whole square. All right. A equal to x power n, where n is a constant. So, what is going to happen here? Sigma A square is going to be given by dou A by dou x the whole square times sigma x square. So, dou A by dou x is going to be n into x power n minus 1. So, this will make sigma A square will be equal to n square x power 2n minus 2 times sigma x square. Let us divide the entire term by A square, that is going to be equal to x power 2n. So, this reduces, we should be able to cancel this and this. So, this will result in sigma A square by A square is equal to n square sigma x square divided by x square. This implies sigma A by A is equal to n sigma x square by x. Okay, sorry, n sigma x by x. Good. I would leave it as an assignment for you to figure out what happens when you want to take A is equal to log of x and let us say A is equal to anti-log of x. Kindly do these two assignments to determine what is sigma A in this case and sigma A in this case as well. So, one is able to understand. Let us take a simple example so that we try to impress upon why is that we are discussing about this. Let us take the ideal gas equation where PV equal to nRT. You realize that let us say you are trying to determine pressure as a function of volume and temperature, and let us say these are the two variables that you have control over, and you have a certain error of measurement that is associated with it. What do we mean by this is that when you are trying to measure temperature, you will be, let us say you are using a thermometer in this case, and your thermometer has divisions that go between say 0.1 degrees Celsius. That means that your measurement cannot be more accurate than the minimum value, the least count that you can use for such a measurement. So, what ends up happening by default, the pressure is going to be having uncertainties from volume and from temperature, but the exact equation of error propagation helps you determine and quantify. If you are able to quantify sigma v and sigma t, you can precisely quantify what is sigma p. So, this is an important part of understanding how errors go forward. In the following lecture, we will be understanding how this will all help us assess what is the true value. So this is how we started the lecture. We were trying to say we are trying to seek the truth in terms of experiments by collecting data. While we collect data, you get something like a mean and a standard deviation, and this standard deviation could be for multiple independent variables that you are varying to get your measurement, and we are able to see through error propagation how finally for a given variable that you want to measure, these errors propagate. Now that we see it, we will try to define what is the true value and what is accuracy versus precision. In order to do this, let us take an example. For this example, let us think that there is an archer who has a bow, and then of course he is trying to use the arrows to pierce into the center of this target. Okay, so what is going to end up happening? Is going to first put the arrow here, and the bow is going to hit it, and we are going to ask, let us say the archer is trying to aim, how far is his aim good? Okay, so this is nothing but the measurement that we are trying to do. Let us assume that our true value exists at the center of this board, and we are the experimentalists. We are getting each one of the data points which can be thought about as the arrows that are being pierced onto the board. How close are we getting to the center of the board? Of course, this depends on how good the archer is able to aim and able to hit the center. So now each of these arrow points is going to be depicted by the black dots on this board, and the red dot indicates what is the mean, the sample mean, and of course if you have many measurements, it is going to become the population mean. What is the sample mean that goes with such an archer aiming in the middle of the board? And you have a bar that comes along with the average. This depicts the standard deviation. So basically you are able to understand is that if the archer is spraying throughout the board, the standard deviation is going to be more, but if you are able to take an average that finally works out to be the center of the board, you are still happy as the average works out to the true value, but you would want to improve it because the spread is a little more. So we will see a few examples for such a scenario. So here you are able to see 4 different boards, 1, 2, 3 and 4. And these cases, let us take a little while to understand what is going on. In each of the case, the true value is represented by the red dot in the center, and the scatter of the black dots indicate where the arrow has hit. And in this case, what you are able to see visually already is that all the dots are close to the center, and there are very few dots that go outside the second circle that is in blue. On the other hand, you are able to see in the second board, the dots are still close to the center, spread around the center, but there are few dots that go really farther away. So qualitatively, one can already say that archer 1 seems to be better than archer 2, largely because the spread is lesser and both average out to be in the center of the board. On the other hand, if you see the true values in the center, archer 3 unfortunately has been able to get all the points concentrated on one side of the board. Unfortunately, it is far away from the center of the board, but still all these values are concentrated on one side. On the other hand, archer 4 is the poorest of all because all the points are spread over in all different places, and even some of them have gone outside the board. And you are able to realize neither you are having all the points being bunched up together, and it's not even spread close to the center. Here is where we are going to be defining the 2 very important parameters of precision and accuracy. So what do we mean by these? Let us say xi is the observed value. This is the way we have been defining it so far, and x is the true value, and x bar is the mean, sample mean that we end up getting. How close is the mean value to the true value indicates accuracy. The more closer x bar is to x, you try to say that measurement is accurate. On the other hand, so let us take one other example. So let us say once again you are trying to measure 2 ml out of a burette, and these are the measurements that you have done, just as the example that we have seen. And this gives you an idea how far you are going away from the mean of all the values that have come up, or rather from the true value that has come up. And then you realize that can I make an assessment that goes with it. Once again, these are the definitions that we have already seen. the sample standard deviation will be given such as this, and if you have large number of data set, that becomes the population standard deviation. So now let's try to define how accurate are archers 1, 2, 3 and 4 with the examples that we have taken so far. Of course, the true value is the center of the board. So now what ends up happening, if you take the average of all these data points which I have done and I am representing by this red dot, you see that it nicely matches with the center of the board, then you say the archer is accurate. And let us say this is the best ever precision one could get, meaning that the archer has not gone beyond the second circle. If you see carefully, almost all the data points lie within the first circle and only a few data points are lying outside. Once again, this makes total sense, because when you are talking about a distribution, you are having almost 66 to 68% of the points falling within the first standard deviation, and 95 points falling within 2 standard deviations, and 99.7 points falling within 3 standard deviations. On the other hand, let us go to the next archer. You are able to see that the points are spread until 1, 2, 3, 4, 5. You even see a data point in the 6th circle, but nicely the average works out to be in the center. But on the other hand, let us determine what is the standard deviation that comes up. You are able to realize the standard deviation is much farther, while in this case the standard deviation was much lesser. So this says archer 2 is less precise than archer 1. Of course, there could be cases where you cannot improve precision. In some cases, let us say the archer is working under very cold conditions and trying to hit the arrow in the middle. Yeah, probably then this is probably the best ever precision one could get. But still, on an average, the archer is still accurate. So now let us go to the next example, where the true value is in the center of the board, that is archer 3, but the average works out somewhere in the center. But if you are able to see, the standard deviation is much smaller than that of the second archer. So this is a case where you have poor accuracy but very good precision. This is a very tricky place to be, because many times when somebody does measurements and keeps getting reproducible values and thinks that is the truth, this is the scenario that is extremely dangerous, because this tends to tell this is the truth, but in reality your truth is very far away from wherever your data points are. So this could be a case we will once again see in the next week why such a case can arise and how an experimentalist can minimize such mistakes to happen. On the other hand, let us see the fourth case. In the fourth case, you see that neither the archer is precise nor accurate. The accuracy and precision are both poor, because the average falls away from the true value, meaning that you have poor accuracy, and the precision is extremely poor, even poorer than what you see here, because you see the width of this is much higher than the width of this. So basically, this is the case where you are inaccurate and imprecise. So this is an example of how badly an experiment could be set up, and therefore neither you get the truth nor you did the setup properly. So basically this indicates this is the worst ever case one can be, and we should strive to make sure we don't end up in that quadrant. And of all the archers, we would like to be the first archer in the case that we are both accurate and precise. And there could be some conditions where we cannot avoid, and it's okay to be second archer where you still get a decent accuracy but poor precision. Of course, we should strive to make the precision better, but the last two cases are something that we must avoid, as it results in poor interpretation of the data and hypothesis, which you will be seeing in the forthcoming weeks that will be handled by Dr. Ashish Srivastava. Thank you.